Okay, so we have a model essentially kind of spelled out. We have an understanding of what human computation is, and we arrived at this kind of understanding via Turing's kind of observation that we have three kind of main components to computation: a control, an executive unit, and a store, and a dynamic kind of loop going between the three, in which the store essentially is more generally can be thought of as like the environment, or in this case of human computation, the paper. And we observe the paper in a particular mental state, and that produces the context. And so the context, just to say again, the context is a particular thing. It's two things together. It's where on the page I'm looking. It's the particular thing I'm looking at on the big page overall, together with my mental state. That's the context. So I observe the paper and obtain a context. And then if I'm following an algorithm, if I'm following like a set of rules that I'm aware, if I'm making a cake and I know I have to do this first and then that second, or if I'm multiplying two numbers, I know I have to do a particular thing in a particular order, then the algorithm tells me, given a context, what I need to do next, right? There is an implied action that must be taken given a context. And that's the second thing I've defined here, action. These two words are going to be used a lot in this coming the next few minutes. So the action is three things, right? There's three things that I need to do given a context, which is I need to write something new at the place that I'm looking. And I am going to assume that I write something new at the place that I'm looking. That's only for simplicity. You could obviously have the action, I could be writing somewhere else that I'm not looking, but that'd be silly, right? I'm going to be writing something in at the little location that I'm staring at. I'm going to be changing that to look somewhere else. So maybe let me draw a picture. I'll say, given the context, I'm right here. Maybe I'll write something in, like sigma. Maybe I'll shift my focus over here. And then I'll go into like a new thought. I'll shift into a new mental state, right? Those three things together, just like the thing I'm looking at in the mental state produce the context. These three actions, these three I think things to do constitute what I'm calling an action here, right? So a context yields via the algorithm an action. And then the action, in turn, yields a new context, right? Because now I have a new context to obtain. And that, in turn, yields a new action. And then you kind of keep going, right? I mean, that's what the loop is, right? We keep obtaining new context and reacting to the new context. And we mentioned that the Turing machine, or this process here, is a dynamical system, which is continually reacting to its own output, its output being contexts. So that's what we've got, and that is almost like a fully rigorous model, at least to the extent that we need it to be for the videos that I'm going to be making here in this little mini-series. But we do need to formalize it just a little more before we can do anything cool with it. Now, I'm going to walk a tightrope here. I need to define a Turing machine semi-mathematically. And I'm going to try very hard not to alienate anybody, because the actual fully rigorous definition of a Turing machine, well, I have a video on that, and it's 45 minutes. So I don't want to make that I don't want to make it like that. I want to just formalize what we've got here just enough that I can make all the major points that I need to make, which isn't as hard to do as I think I made it out to be initially in the first time I gave this talk. So what we want to do now is we need to formalize this a bit. And by that I mean like settle on some stuff, some specifics. There's more to it than that, but what we really have is given a particular. So what we need to define a Turing machine is really what we need to do. So let me put it this way. If I'm doing this with a purpose, right? I'm multiplying two numbers. I'm row reducing a matrix. I'm searching for a word, right? This picture here is general, but this guy here is doing something specific. And what we're going to basically say is that there is going to be a particular, for any particular task, let me put it this way, for any particular task, being done this way, we essentially have a machine. In other words, the person, paper, pencil system, if it, there's a particular person, paper, pencil system which does addition. There's a particular person, paper, pencil system that does row reduction of a matrix, etc., right? So we want to have a system for each of those. And so what we want to define is we want to mathematically define what one of these systems is. And we'll call them Turing machines. So a person, paper, pencil system, which, let's say, adds two numbers, constitutes a particular Turing machine. We're going to call these things Turing machines, these systems that do a particular task. So again, it's attempting, machine. We're not thinking yet about any vacuum tubes or transistors or anything. We're thinking about this, but we are going to call this system nonetheless a machine. And we're going to call it a Turing machine because Turing is the inspiration for it, right? So that's what we're going to do. And so that's what a Turing machine is. And what we want to do is we want to formalize that into math a bit. So to formalize our model and define a Turing machine, we need the following. We need two things. So the first thing we need is we need a standardized way of specifying a particular Turing machine. So I want to standardize the way that I give you something. So I want to be able to, like, basically, what do I need to hand you in order for you to have a particular one of these person, paper, pencil systems that does something? So I need a standardized way of handing you one of these systems and having given you a complete, like, description of one. And so that's going to be syntax. That's essentially giving you we need to standardize the syntax for a Turing machine. And then two, we need a standardized way of thinking about how a Turing machine will operate, which we've already done most of the work in, right? That's semantics. So basically, I want to be able to hand you a particular Turing machine and give you all of the information that distinguishes this Turing machine from any other Turing machine. And then we want to make sure that we have a very kind of spelled out standard way of interpreting how these machines really work, which, again, we've mostly done that already. We just need to make it much more clear. And so those are what I'm going to do in this I don't know if I'm making this a separate video, but yeah. So we'll start with one. Start with one. So to specify a Turing machine, and again, remember what I'm talking about when I say Turing machine is I'm talking about a particular person, paper, pencil system. A Turing machine, i.e., to give someone everything they'll need to have a full algorithm, a full system. We need to give them three things. So here are the three things. I'll just write them. So one, we need to give them a set of mental states, obviously. So the mental states here, I'm going to redraw the picture here. So this thinking emoji thing here, basically what I want to do is I want to sort of discretize the mental states and say I'm going to be in a particular mental state at any moment, and I'm going to index them in a set. So I'm going to call the mental states Q. And in set notation, basically, Q is the set. What I'm saying here is that Q is the set containing Q1, Q2, ... Qn. So these are all the mental states. At any point, I'm in one of these, right? Maybe Q1 is the state that maybe I'm adding two numbers, and Q1 is the mental state which says I am currently carrying the 1, right? That's maybe I have a mental state for that, right? I am currently doing this or that. That's what the mental states are, and I'm going to have a set of them, and it's going to be finite. So that's number one. Number two is a set of symbols. It's things that I can print on the page. So basically, in terms of 2, this here in the area of focus, I'm going to write something here, right? And I'm going to basically say that the set of things that I can write here, set of things which can be written in the area of focus at a given step. So at any step, I'm given a context, and the action is going to be to write something here. And so I want to be able to, I need to specify the set of, I'm going to call them symbols. They don't have to be symbols. They could be like pen strokes, right? Maybe I'm drawing something. But nonetheless, I'm going to call them symbols anyway. The set of symbols sigma, I'm going to call this a sigma, is called the alphabet. It's called an alphabet. It's not the alphabet. It's not the English alphabet. I mean, it could be like ASCII, right? It could be Unicode. But it is a set of symbols that I can print here. And so implicitly already you're starting to get the sense that this paper has more structure than I have been honest about. It's graph paper, right? Because there's only a finite, again, this is also going to be finite. So Q and sigma are both going to be finite. And so the only thing left to specify that this is graph paper now is to make a specification that when I shift my focus, it's got to be in like a discrete number of directions. But of course that's going to be the case. And also, of course, that really isn't going to take away from any algorithmic capabilities, right? I mean, you can do all the algorithms that you can do, that you think to do, you can do them on graph paper. And you can approximate like more smooth algorithms just by using more graph paper. So it's really not a stretch to limit the number of directions that I can go into 8. In fact, maybe I'll go ahead and say that. No, I'm not going to say that right now, but we will do that. I'm basically going to limit it that the focus can either go this way or this way or this way or this way, etc. So I need to specify those two things. What symbols am I going to be printing on the page, and what mental states will I be shifting into and out of? And those are the two kind of simple ones. And then 3 is the big one. 3 is the most important one. I need to specify a set of instructions. Instructions are going to take the following form. Instructions take the form of, given a context, do this action. In other words, they're basically, for every context, I'm going to have an instruction that tells me what to do with that context. Obviously, we need that. In order to specify this as a machine, then I need to basically give you a thing to do for every context. And if I give you a thing to do for every context, if I give you an action for every context, then I've given you a complete dynamic system that you can kind of imagine working its way and doing its thing, right? So let me go ahead and specify some specifics about these instructions. I'm just going to kind of make this a bulleted list. There needs to be one instruction for every context. Obviously, more than one instruction for every context would be weird, although we do, some people do mess around with that. Including myself, those are non-deterministic Turing machines, but there needs to be, let's just say, there needs to be, for this system, there needs to be one instruction per context, meaning that if I didn't make the set of states and the set of symbols finite, then I wouldn't be able to give you a complete set of instructions in a finite string of text. But if I do make these two things finite, then there's only finitely many instructions that I need to give, right? If Q has 5 things in it, if there's 5 mental states and 26, or let's say 25 because I can't do any multiplication, 25 symbols, then that amounts to 125 instructions that I need to kind of specify, right? Because there's one for every, for every state there's however many symbols. So in order for them, so I'm going to assume finitely many states and symbols. So the finitely many symbols is probably something that everybody can accept without really any philosophical justification, even though I'm going to give some anyway, because they're used to that. When you are doing an algorithm on paper, you're using English letters and digits and maybe some Greek letters and maybe some like fancier symbols like you're using maybe plus in the integral sign, stuff like that, right? But it's finite, right? You have a finite alphabet that you tend to work with. And the reason that that's not a really big deal, philosophically, to justify that further, suppose I run out of symbols. What do I do then? Well, I just use two boxes, right? Just use the same symbols and just have two boxes. Suppose I only have two symbols, right? Suppose I only have like 0 and 1. How do I, if I need a third symbol, then I'll just use two boxes and then call the pair in those two boxes, just see that as one symbol, and then that's fine. I have infinite paper, right? So as long as I have infinite paper, I can just chain together symbols and say that's one symbol now, and then just work that way. So finitely many symbols is no big deal. Finitely many states is also no big deal, because consider this, right? If the machine halts, and keep in mind that Turing machine operation is pretty clearly discretized already, right? Just look at the picture we drew. There's a discrete step, just kind of in this context action response framing. We have like discrete steps of the computation, right? And so any computation that finishes doing something and halts, i.e. the useful ones, they're going to only use a finite number of steps. And so if I only have a finite number of steps, then I'm only going to use a finite number of states. Now that's not a full justification, because I need the number of states to be constant for any computation that I'm doing. But that does kind of go in the direction of saying, it's fine to assume a set of mental states that's finite. So yeah, I might leave it at that. You might be kind of worried about a finite set of mental states. You probably aren't. I'm probably the only one that is. But maybe we'll return to that. But we are going to assume a finite set of states and a finite set of symbols. And then since that's the case, we can now say that we only need a finite set of instructions. So before I say that, though, I should repeat, assume we have infinite paper. And by infinite paper, I really mean that I don't have stacks of paper. What I really have is a grid, an infinite grid. And also, it's a grid. By that I mean the number of I'm going to limit the direction that the focus can change. So i.e. the focus is limited to moving around on a grid. So it's graph paper. In other words, when I specify kind of an action, that is kind of say, when I specify like an action, I'm going to basically specify a direction to move the focus in, and it's going to go either this way or 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 this way, or stay still. So finitely many directions that I can possibly be moving in. And so with all of this assumed, also, by the way, another thing I should mention is keep in mind that in order to kind of have a set of instructions, I need to be able to say, like, what's my context? And it's entirely possible that I'm looking at a blank space. So another point I need to make here is it's possible to be looking at a blank space. Thus, blank is a symbol, is seen as a symbol, which is common to all alphabets. So I'm going to assume that blank is a symbol so that I can kind of interpret these instructions as taking like a symbol and a state and then giving an action based on that symbol in that state. I could be looking at a blank space, so I got to interpret that as a symbol. And so with all of this assumed, we can specify a Turing machine. We only need finitely many instructions to fully specify a Turing machine. And hopefully you agree that those assumptions are pretty innocent overall. And by innocent, what I really mean is that we haven't lost any computational power by doing that. The human computation has not been weakened by making any of these assumptions. Hopefully you can agree with that. So I'm going to call the set of instructions delta. So I have, so call the set of instructions delta. And I'm going to try to avoid the notation here. I'm trying to try to avoid saying this as notation, but maybe I should probably say it as notation. So instructions. Okay, so let me go ahead and start over. So I'm going to call the set of instructions. Well, okay. So to summarize, specifying a Turing machine, to specify a full kind of human paper pencil system, I need 3 sets. I need a set of states, Q, and I can write Q as like, Q1, Q2, ... Qn. A set of symbols, sigma, and this is a capital sigma, and then I'll kind of use lowercase sigmas, sigma 2, ... sigma m, and a set of instructions. And this is going to be a lot bigger of a thing than these two guys. And I'm going to call the set of instructions lowercase delta. Delta is technically a function. It's a transition function. That's what it tells you how to transition from one step to another. And an instruction kind of, let's give it a common form so I can think about it more kind of mathematically. Instructions look like quintuples. Like a set of 5 things. Why is it a set of 5 things? Because a context consists of 2 things, and an action consists of 3. So if I want to specify a full instruction, then I need to specify five things. Given these 2 things constituting the context, these 3 things are the result, and those constitute the action. So let's kind of see what that looks like. So basically, given a context, which is, let's say, a symbol sigma and a state q, and these 2 things together form the context, the pair is the context, delta is going to take that context to an action, which is 3 things, which is a new sigma, I'll call it sigma prime, a new state, call it q prime, and a direction, call it d. And so the quintuple can look like this. So just kind of put it all together. So say an instruction is of the form sigma, comma, q, comma, sigma prime, comma, q prime, comma, d. And so that's what they look like. And so sigma is basically the set of all of these, where we're going to have one of these for every sigma q pair. In math notation, you would basically write that the transition function is a function from sigma cross q to sigma cross q cross d where D is basically the set, you know, up, right, left, or right, you know, this way, just all the directions. And then also a don't move option. So it's the set of directions. But that's not important. Don't worry about this. But it is a function. It's a function from this area domain to this codomain. Okay. So that's what the set of instructions looks like. It just looks like a bunch of quintuples. And so if I give you those three things, then I've given you a Turing machine. So here's the mathematical definition. A Turing machine, I said Turing machine again, is a triplet. And I'm going to denote it M for machine, and it's equal to the kind of the set Q, sigma, Q, delta. If I just give you those three things, then I've syntactically given you a Turing machine. And I've given you every, and keep in mind, this is one long string of text. This, so very important to note that this, and the whole reason I'm actually defining it in this detail is to note that this, it can be specified, be written down entirely as a finite string of text. Much like a program that you would hand somebody or write in a language, right? In a programming language. Much like a program you'd write in a programming language. In fact, it's exactly like that. And it is, but it is important to it's important to realize that we can specify it finitely. We can finitely specify an algorithm, and that is one of the defining features of kind of an algorithm. Because if you know, infinite algorithms don't really make sense to talk about.